Somewhere in the American West, a train is moving through the dark. You probably can't see it. You might not even hear it until it's almost past you. But if you happen to be standing near the tracks when it goes by, you will feel it. In your chest, in the ground beneath your feet, in the fillings of your teeth. It is not a fast train. It doesn't need to be. What it is heavy. Almost incomprehensibly heavy. A single loaded coal hopper car on an American freight railroad can weigh around 143 tons. That's one car. A typical unit coal train hauls 100 of them, sometimes more. Do the math, and you're looking at a moving object that weighs somewhere in the neighborhood of 15,000 tons, crawling across the landscape at 40 miles an hour, held to the earth by nothing but steel wheels on steel rail and the sheer arithmetic of friction. No passenger train comes close. No freight train in Europe comes close. No freight train anywhere else on Earth routinely operates at these weights. The United States runs the heaviest freight cars on the planet, on a network that stretches for hundreds of thousands of miles, and most people have never once stopped to wonder why. It didn't happen by accident. It didn't happen because American engineers were reckless, or because regulators weren't paying attention. It happened because of geography, because of economics, because of decisions made over a century ago that locked an entire continent into a particular vision of what a railroad should do and how it should do it. That vision produced something extraordinary. A freight system that moves more goods, over more distance, more cheaply than almost anywhere else on Earth. It also produced trade-offs that nobody likes to talk about. This is the story of why America's freight trains are built the way they are, and what it actually costs to move that much weight across that much land. To understand why American freight cars are built so heavy, you first have to understand the sheer scale of the system they operate on. Because the numbers, when you actually sit with them, are almost difficult to process. The United States has roughly 140,000 miles of freight railroad track. That is not a typo. 140,000 miles. Laid end to end, that track would circle the Earth more than 5 times. It would reach more than halfway to the moon. No other country on Earth comes close to that figure. China, which has invested staggering sums into its rail network over the past 2 decades, operates a freight system roughly 1/3 the size. The entire European Union, with 44 countries and hundreds of millions of people, has less freight rail mileage than the United States does on its own. And this network is not decorative. It works. American freight railroads move roughly 1.7 trillion ton-miles of cargo every single year. A ton-mile is 1 ton of freight moved 1 mile. And that figure means that if you added up every ton of every commodity carried every mile across every railroad in this country, you would arrive at a number with 12 zeros in it. Coal, grain, automobiles, chemicals, lumber, intermodal containers stacked too high on flat cars. All of it moving continuously, 24 hours a day, through mountain passes and across river bridges and over plains that go on longer than some countries are wide. What makes this even more remarkable is that it runs almost entirely on private money. Unlike virtually every other major freight rail system in the world, American railroads are privately owned and privately operated. The companies that run these trains also own the tracks they run on. They pay for the infrastructure. They pay for the maintenance. They pay for the locomotives and the cars and the crews. There are no government subsidies propping up the freight side of the ledger in any meaningful way. The whole enterprise has to pay for itself, and it does, but only because it has been engineered from the beginning to move enormous amounts of freight at the lowest possible cost per ton. That last part is the key to everything. Cost per ton. It is the single metric that has shaped nearly every major decision in American freight rail history, from the width of the track, to the height of the tunnels, to the weight limits, that allow those massive cars to roll legally on that network. When you are operating at this scale, across these distances, the economics of freight movement become ruthlessly specific. Shave $1 off the cost of moving a ton of grain from Kansas to the Gulf Coast, and you have changed the math for every bushel of wheat grown in the American interior. Scale that across 1 trillion ton miles, and you begin to understand why the people who built this system were so relentlessly focused on capacity, and why heavier cars, carrying more per trip, became the foundation of an entire philosophy. So what does heavy actually mean when we are talking about American freight cars? Because the word gets used loosely, and the reality of the numbers has a way of stopping people cold when they first encounter them. A standard modern covered hopper car in the United States, the kind you see carrying grain or sand or plastic pellets, is built to carry a gross weight of 286,000 pounds. That is the car itself, plus its load. The car body weighs somewhere around 30,000 pounds empty, which means the cargo alone can clock in at roughly 115 tons. One car, sitting on 4 axles. Rolling down a track on wheels not much wider than your hand is long. Now put that in context. The standard load limit used across much of Europe sits closer to 22 or 23 metric tons per axle. The American standard is 32.5 short tons per axle. That gap is not a rounding difference. It represents a fundamentally different calculation about what a railroad is supposed to do and what the infrastructure underneath it is supposed to tolerate. And American railroads have been pushing that ceiling steadily upward for decades. There was a time when 263,000 pounds gross was the standard. Then the industry moved to 286,000. Right now, there are ongoing efforts to certify cars and track for 315,000 pounds, a threshold that would have seemed reckless to engineers working even 30 years ago. Some specialized cars, the kind hauling coal out of Wyoming's Powder River Basin, already operate at those weights in controlled corridors where the track has been specifically reinforced to handle them. To put a finer point on it, a fully loaded American coal train running 150 cars weighs somewhere in the neighborhood of 27,000 tons. The locomotive consist pulling it might stretch 600 feet on its own. The train behind it stretches for over a mile. The total force required to get that mass moving from a standing start is almost beyond intuition. Structural engineers who work in other industries sometimes encounter these numbers and have to sit with them for a moment. The cumulative pounding that a piece of track absorbs under that kind of load, repeated day after day, year after year, is staggering. Steel fatigues, ballast shifts, ties split. The whole system is engaged in a slow, continuous war against the physics of what it is being asked to do. And yet it keeps working. Trains keep running. Which raises an obvious question. How did America end up here, operating at weights the rest of the world looked at and decided were simply not worth the trouble? The answer starts in the 19th century, and it starts with geography. When American railroads were being built, the continent they were crossing was enormous, in a way that European engineers simply did not have to reckon with. The distances between resources and markets in the United States were not measured in dozens of miles. They were measured in hundreds, sometimes thousands. Coal seams in Pennsylvania needed to reach furnaces in Ohio. Timber from the Pacific Northwest needed to reach cities on the Atlantic seaboard. Grain from the Great Plains needed to reach ports on the Gulf of Mexico. The sheer volume of raw material that an industrializing America needed to move was staggering, and it needed to move cheaply, because the margins on bulk commodities are thin and the distances are punishing. In Europe, the calculus was different. Countries were smaller. Competing modes of transport, canals, rivers, coastal shipping, remained viable alternatives over shorter distances. The political geography meant that rail networks crossed borders frequently, which created pressure towards standardization and compatibility. Lighter, more uniform rolling stock was easier to manage across systems that had to cooperate with each other. And European governments, which often owned or heavily regulated their rail networks, had reasons to favor passenger service alongside freight, which pushed toward infrastructure designed for speed and smoothness rather than raw tonnage. America had almost none of those pressures. What it had instead was private capital chasing profit across a continent that rewarded whoever could move the most bulk at the lowest cost per ton mile. That single economic reality shaped almost every engineering decision that followed. Early American railroads were already building to heavier standards than their British counterparts. Heavier rail, wider spacing, more robust car designs. It was not a grand plan. It was a series of individual decisions made by individual railroad companies, each one trying to squeeze more capacity out of a system that was perpetually struggling to keep up with demand. And because the American railroad industry was fragmented among hundreds of competing private companies, there was no central authority to pump the brakes. If one railroad figured out how to run heavier cars and undercut a competitor on freight rates, every other railroad on the continent had a powerful incentive to follow. This created a ratchet effect that ran in only one direction. Weights went up, car capacities increased. Track standards were upgraded to handle the new loads, which then allowed weights to go up again. The railroads lobbied federal regulators, and largely succeeded, in convincing them that higher gross weight limits were in the national economic interest. The argument was not unreasonable. Cheaper freight rates meant cheaper goods. Cheaper goods meant a more competitive industrial economy. The logic held together well enough that load limits climbed steadily through the 20th century, from 263,000 pounds to 286,000 pounds, and then into the experimental territory beyond that in certain high-volume corridors. What was never fully accounted for in that calculation was the cost being quietly externalized onto the infrastructure itself. Every time the load limit went up, the track paid for it. Bridges paid for it. Wheels and axles paid for it. The war against physics that the previous numbers described, that war was the accumulated consequence of a century and a half of decisions made by people who were optimizing for the cost of moving freight, not the cost of maintaining the system that moved it. The two things are related, of course, but they are not the same thing, and the gap between them is where a great deal of American railroad history quietly lives. So how do you actually build something that survives that war? How do you design a rail car, a wheel, a rail, a bridge, knowing that the forces bearing down on them are among the most punishing on Earth? The answer is that you engineer everything thicker, harder, heavier, and more redundant than almost anyone else in the world would consider necessary. And then you accept that even that will not be enough to stop the slow accumulation of damage. You just try to stay ahead of it. Start with the cars themselves. American freight cars are built to a standard called the AAR plate, maintained by the Association of American Railroads, which specifies the maximum dimensions and structural requirements that rolling stock must meet to operate across the network. The cars are massive steel structures, designed not just to carry load, but to transfer that load safely through couplings, because trains are pulled, not just pushed, and the tension running through a long freight consist is itself an enormous mechanical force. The couplers on American freight cars are correspondingly enormous. They are designed to handle hundreds of thousands of pounds of drawbar pull without failing. When a heavy unit train accelerates, those forces are staggering. Then there are the wheels and axles. American freight wheels are large diameter cast or wrought steel components rated to specific load limits per axle. The standard 4-axle freight truck, the assembly of wheels and axles that sits beneath each end of a car, must distribute that enormous gross weight over those 4 points of contact, each one no larger than a coin. The contact patch between a steel wheel and a steel rail is tiny. The pressure at that point, repeated millions of times per year on a busy main line, is what drives rail wear, wheel wear, and eventually fatigue cracking in both. Engineers know this. They plan for it. The metallurgy of rail steel used on high-traffic American corridors has been continuously refined over decades precisely to resist that kind of contact stress. The track itself is engineered in layers. Heavy rail, meaning rail with a higher weight per yard, is used on main lines carrying the most tonnage. Beneath it, the tie and ballast structure is designed to spread load broadly enough that the subgrade beneath does not fail. Concrete ties have increasingly replaced timber ones on the highest stress segments because they resist the lateral and vertical forces better and last longer under repeated heavy loading. And bridges. Every bridge on a heavy-haul corridor carries a load rating, and those ratings must be maintained against the constant degradation that heavy axle loads produce. Old bridges get retrofitted, new ones are built to higher standards. The inspection regimes are continuous. None of this is cheap. None of it is simple. And none of it fully solves the problem. It only manages it. The infrastructure is not winning the war against physics. It is surviving it year by year through investment and maintenance and engineering ingenuity, while the loads it carries remain, by global standards, almost without parallel. But surviving is not the same as thriving. And that distinction matters more than the freight industry sometimes likes to admit. The heavier the car, the more damage it does to the track beneath it. That is not a theory. It is a mathematical relationship, and it is brutally unforgiving. The damage a wheel inflicts on a rail does not scale linearly with axle load. It scales roughly with the fourth power of that load, which means that if you double the weight on an axle, you do not double the wear on the track. You increase it by something closer to 16 times. That single fact explains why American railroads spend enormous sums on maintenance every single year, sums that would strike most people as almost incomprehensible for what is, at its core, a network of steel sitting on gravel and wood. The figure most commonly cited by engineers is this. Track maintenance costs in the United States run into billions of dollars annually across the major Class I carriers. Union Pacific, BNSF, CSX, Norfolk Southern. Each of them devotes a staggering share of their annual capital expenditure just to keeping the existing infrastructure from degrading beneath the loads they themselves are placing on it. It is, in a very real sense, a treadmill. The heavier the trains, the more revenue they generate, and the more that revenue is consumed by repairing what those trains have done to the ground they run on. And then there is the question of speed. Heavy freight cars and high speed are fundamentally in tension. The physics that allow a 150-ton car to survive on American track also demand that it move relatively slowly. Faster speeds amplify dynamic forces, the bouncing and hunting and lateral surging of heavy rolling stock, in ways that would destroy both equipment and infrastructure far more rapidly than even the current maintenance burden suggests. American freight trains average somewhere around 25 miles per hour across the network. That is not a failure of ambition. It is a consequence of mass. Passenger trains share some of these corridors. And this is where the trade-off becomes visible in a way that ordinary Americans actually feel. When freight infrastructure is optimized for maximum axle load and maximum tonnage, it is simultaneously being de-optimized for the kind of smooth, well-maintained, geometrically precise track that passenger trains require to run fast and ride comfortably. The two goals pull in opposite directions. You can have heavy freight, or you can have fast passengers. Doing both on the same track at the same time is one of the defining infrastructure headaches of American railroading. It has been that way for decades, and the heavier the freight gets, the sharper that tension becomes. So if this system carries such staggering volumes of freight, if it moves more ton-miles of goods than any comparable network on the planet, why didn't the rest of the world simply copy it? The answer is not that other countries failed to notice what America built. They noticed. They made a different calculation. In Europe, the decision was made early and reinforced repeatedly that railroads would serve two masters simultaneously, freight and passengers, and that passengers, with their demand for speed and ride quality and punctuality, would set the terms. European track standards evolved around that priority. Axle loads were kept lower, not because European engineers lacked ambition, but because heavier axle loads and high-speed passenger operations are genuinely incompatible over the same infrastructure. You cannot brutalize a rail with a 100,000-pound axle and then run a tilting express train over it at 200 kilometers an hour. The geometry deteriorates too fast. The ride becomes rough. The maintenance intervals compress. The economics stop working. Japan went even further in the other direction. When the Shinkansen was designed in the late 1950s, the engineers essentially started over, building a dedicated high-speed network with no freight traffic at all. The track was protected from heavy axle loads entirely. That protection is precisely why the system can operate with the reliability and speed that made it famous. The trade-off was explicit and deliberate. In Australia, parts of the network did follow a heavier haul model, particularly in the iron ore regions of Western Australia, where the economics look more like American coal corridors than like European mixed traffic lines. Those operations run in geographic isolation, moving bulk commodities from mine to port, with no passenger trains complicating the equation. The conditions that made American heavy freight rational, continental distances, bulk commodities, minimal passenger pressure, were replicated in miniature, and the result was similar. What the rest of the developed world recognized is that heavy freight and passenger rail are not just different services. They are different engineering philosophies, and blending them requires constant compromise that ultimately serves neither goal as well as a dedicated system would. America never fully confronted that choice, partly because passenger rail atrophied to the point where it could not effectively push back, and partly because the freight railroads owned the infrastructure and had every incentive to optimize it for their own traffic. The world did not fail to follow America's example. The world looked at the full picture, the axle loads, the slow average speeds, the track punishment, the passenger consequences, and concluded that the trade-off only made sense under a very specific set of conditions. Conditions that, outside a handful of places, simply did not exist. And that is what makes American freight rail so fascinating. It is not a universal solution. It is not even an obvious one. It is a system that evolved under a very specific set of pressures, on a very specific piece of geography, over more than a century of incremental decisions that compounded on each other until reversing course became essentially impossible. The heaviest freight cars on Earth exist because of coal and grain and distance and the absence of political will to protect passenger rail from the consequences. That story has layers that go far deeper than axle loads and track standards. If you found this one worth your time, there is a great deal more to explore about the infrastructure choices that shaped modern economies, about the engineering trade-offs hiding in plain sight, and about the rail systems that took entirely different paths and why. Subscribe, and we will keep going.